Welcome everyone, and I'm very pleased to have three guests here on this panel discussion. We have Geoff Lee, Senior Vice President and General Manager for Microcontrollers at NXP, Jens Stapelfeld from Xilinx, he's Business Development Manager, and Jim Tung, some of you may know him from the keynote yesterday. He's with Mathworks and he's a fellow, so he's a very experienced person. For the German audience, a fellow is a person who has no responsibility for leading a division, but he has the freedom to develop strategies. And we will talk on artificial intelligence today, as everyone talks on this trade fair show. So there are very well-known examples of AI applications like autonomous driving and medical imaging, where you can detect things like cancer. But as we see so many activities in the AI area, I would like to know, what are your customers doing with AI? There must be much more. Geoff?
Well, clearly machine vision is one of the leading application areas in all its forms, whether it's from automotive vision or from object recognition in industrial systems. Mm-hmm. But there are many different scalable levels of machine vision. Mm-hmm. Next would be voice recognition and natural language processing. Mm-hmm. And lastly, we're seeing more and more in the area of anomaly detection. Mm-hmm. So machine monitoring and maintenance, as well as preventive.
Mm-hmm. Jens, do you have additional
well, I think this is the main ones, definitely, and it's not surprising that we have in Germany automotive and machine vision and these things going. We start having discussions with customers about predictive maintenance and analytics about all this data in fabrics as well. So this is very interesting topics. We have some interesting demos on our booth around this as well.
Mm-hmm, mm-hmm. I think when you look at AI, I mean, you look at also the machine learning aspects, not just deep learning. And so it extends from vision onto other types of data models as well. So if we think about machine learning, it also appears in even areas like mining, copper processing, and things like that. And I think when you look at deep learning, certainly a lot of the natural applications that have been most proven have been in vision systems, as you say. But as people are doing more work with transformations of sounds and acoustics and text into a representation that can be consumed by deep learning, we're seeing the examples move beyond the normal vision types of applications.
Our topic here is AI on edge devices. There is a relatively broad definition what an edge device could be. Let's say an embedded device of any kind, in contrast to AI in cloud centers. So my next question would be, how far can we go down with the hardware resources, or what can we do with a certain hardware like a advanced microcontroller? What is possible on the edge, on the device, in the field with applications? You may give me examples what to do or what to apply on these devices today.
Well, I think we have to make a distinction between an edge device and an end node. Mm-hmm. An end node would be the definition of a device which is attached to a sensor, or simply an end node in itself. Mm-hmm. Edge node can be the same thing, and it can also be the aggregation of a number of end nodes, but it's less than a gateway, less than a full gateway. And I think the scale of processing, firstly, it's changing so rapidly that we can see orders of magnitude increase in processing compared to the typical cost of an end node or an edge node a few years ago. So what's possible is really time, changing very quickly with a very fast runway.
There's an interesting terminology issue, because I think that's a great definition. I think when I talk to customers, actually they think of the edge as almost anything from the gateway, all the way up to maybe a server class machine working with industrial machinery to do optimization with actually fairly dramatically large storage and processing capabilities. But I think if you stay in the constrained area, right, to the embedded systems and how you want to describe the edge nodes, I think it's interesting the algorithmic changes that are taking place to try and take, let's say, deep learning networks and shrink them. Yep. Let them run on limited processing, limited memory, maybe making use of remote services to do a lot of the training, but where the application of the inference model is done in a very tight manner.
Xilinx has no general purpose processors, but FPGAs, so you have special hardwares. Do you have more opportunities to process II because you can adapt the hardware?
Definitely, I think that's the edge is definitely very much in the domain what we are doing with the flexibility and latency and low power, adapting the networks. And if you look at the papers coming out in the moment, a couple of years ago it was all about big processors and data centers. Today we see so many papers about squeezing small networks into FPGAs and going even from the bit rates down from floating point down to 8-bit, or we have in our research center in Dublin, we have binary neural networks. We can do neural networks on below 1 watt or 2 watts, which are very specific for things on the edge.
I think there's a broad definition of accelerator. Yeah. So you can see accelerators which are nothing more than Mac or assemblies of Macs that can be applied on the coprocessor interface of an MCU, through to various scalable DSPs. 10-silica is a good example of scalable DSP across a wide number of ranges, right through to scalable GPUs. And then at the high end, you have the dedicated, now we're in the third generation of dedicated AI accelerators.
Yeah, I think in a funny way, there's almost too much choice,
yes,
right? Because you have the choice of, the half precisions, the int4, that kind of level of compute. In which case, the programmable fabrics are wonderful. You have the issue of, I've already got a processor in my system. What can I reuse by adding an accelerator, or just by using the bandwidth on the MCU? So in a way, it's a question of, I've got a problem to solve or an application to apply. What's my decision tree for how do I get to what should go where? That's today not an easy choice.
We're also seeing a move from homogeneous accelerators, just single point accelerators, to heterogeneous distribution of the task across all the resources in an SoC.
And also off the SoC.
But now we have a problem. How can software vendors deal with all this variety of hardware? Mathworks, as a software vendor, has tools to generate neural networks. How do you deal with this huge zoo of hardware architectures?
I'll call it an array, not a zoo. I think the way we've always approached it in our embedded systems, part of our business, is to try and combine abstraction in terms of how the algorithms are described, automation in terms of how the code is generated, and then making sure that the code generation can make use of optimization of libraries. And so you get the nice abstraction so that the designer doesn't have to care about what the target is. They can defer that choice if they want to. But at the time of binding, at the time of code generation and binding, they can make use of the optimized libraries to make sure that it's target specific in implementation. The interesting thing that we've done also with actually both is to try and close a loop so that as you're trying to come up with the design and you want to tailor it to a certain target, you get some feedback about what resources are, what the performance could be, so that if you really are locked into a target from the beginning, you actually can make that part of your design criterion, which is nice.
Abstraction is that a concept you like? Because I would assume that hardware vendors would more like to keep their customers in a hardware lock-in. Wouldn't it be a better idea to develop your own development tools, like you do, by the way?
Well, we do. I think customers have a primary choice of their classification and training environments, whether that's TensorFlow Lite, or Caffe, or one of a number of cloud-based environments. One of our roles is to provide optimization and scalable implementations so that a customer can decide what depth of the total training model he wants to implement, what are the time parameters, what are the constraints in the local system. So I think the onus is on the hardware vendor to provide at least the optimization tools, but we don't intend to lock people in from the point of view of which environment they use for training.
Yeah, that's very much our goal as well. We have invested very heavily in software and work with our partners to raise the abstraction level, but we know best what's working in our hardware, and so we provide the middle layer for these applications, and so that we can go into the frameworks and use the frameworks and optimize that for our hardware. And that's definitely what we continue to invest in as well.
There's also the element of customers who have very low knowledge of deployment of machine learning in the application, and what they're really looking for is a fast, easy-to-use system that gets them some level of capability.
Yeah, I think that's an interesting point, because I think from our perspective is to try and get as many people to know what the AI methods can be, and then figure out as fast a track to get them to silicon, and then in a way it's beyond our choice, if you will, about which silicon they choose and how they combine it. So in a way, we want there to be a very big funnel at the beginning, and then how they make their choices is up to them and to these guys.
Now, from this quite specific question, I want to go back to a more general topic. If you follow the industry for years, you see waves of developments. First, we have seen the PC area, then the server area, then we have seen the smartphone rise up and the cloud area. So it's always a change between centralized computation and device-centric computation. So today, edge computing is the term of the day, and what is your perspective for the future? If all edge devices are AI enabled, will we see a wave back to a more centralized approach?
I don't think so. I think we're looking at what's called the third disruptive era. Yeah. Jeffries call it that. It's the fourth wave of computing. And in each wave, the number of devices has multiplied by a factor of 10. And so this wave is going to have so many distributed edge devices, even more than the mobile handset era. Yeah. Just the sheer data involved and traffic of data and management in data center precludes that all data would be managed in the cloud. So there's going to have to remain to be a balance between distributed edge and cloud processing.
Yeah, there needs to be some in between processing and before you go into the cloud again, and so that replies being in latency. There are some applications you can't just send the things in, and with the volume of data we just produce with all the sensors on the edge, it's just simply not possible.
I think it's it becomes a non-question away, because it's not a matter of always embedded or always centralized. It's a question of where you distribute. And part of the challenge is that the locus of control moves beyond the embedded engineer or the systems engineer or even the engineer, because all of a sudden you've got to involve the IT guys and the OT guys who have their own view of where the data should live, and then you get into negotiation. Negotiation of who owns the data, what the security should be, and where should it live in order to make the right decisions.
You also have to take into account the connection, standard, speed, and what's the default state, how much computation, how much processing continues, even without the context of the cloud. So very few systems can have the kind of up reliability of being 100% guaranteed connected.
Yeah, that's true. For the round up of this discussion, I would mention a thing that I would like to call secondary effects of artificial intelligence. Maybe we can see an image here on the screen that we had on our daily newspaper for the first day. It's a portrait of Tung. If you could turn around, please, to see the audience. This is a portrait.
This was early in the morning, just to be clear.
Not only early in the morning, but it was generated by a Van Gogh filter for the Netherlands painter. And if you may have followed the news, there was an auction in London where a AI-generated painting was versteigert. Was heißt das? Auctioned.
Paid off, yeah.
And it generated a lot of money. But the second question that arose was, who has the copyright of that image that no artist ever touched? Or, for example, Huawei of China has generated music to finish Schubert's Unvollendete. That's a symphony that Schubert never finished, and that algorithm was trained on the music that existed and finished that symphony. So a very similar topic. Here for the embedded industry, what would you think are
Thank you.
are implications that AI may have in terms of how will we use devices in the future? Will we talk to any device, or what may we see in the future?
Okay. I think in the longer term, a lot of embedded devices today, standalone, non-connected devices, come fully programmed with control algorithms, everything fully validated. If we really extrapolate to a fully AI, we'll see something similar in the way that human or mammalian young evolve, in that the system may be only partially complete at delivery, and that the system can actually learn and become more complete as it matures. So that would change the whole paradigm of programming devices. As opposed to just AI being used for a portion like machine vision or for voice, it could apply to the entire functionality of the product.
In the research area, there's an area called Cyberphysical systems. And a lot of that has to do with this somewhat arbitrary connection of things that are designed partially, but then combine. And an interesting concept in CPS or Cyberphysical systems is the idea of emergent behavior, where the behavior only happens when multiple devices are in proximity and interacting with each other. And so all of a sudden the value proposition becomes the credit for the value doesn't go to a single system or even to a single author. It is through the collaboration of these devices, perhaps with multiple authorship.
That's an interesting variant of Metcalfe's law, which is that the value of a network increases proportional to the square of the number of devices.
Yeah, it's definitely very interesting, and we will for sure see new things and innovations coming up. I can't comment or know where that is going, but there will definitely be some very interesting stuff coming out of that.
In any case, Geoff, what you mentioned was very interesting, because I heard the same from IBM. They said those AI systems will not get older, but they will get better as longer they exist. So that may be the first generation of computers that really improve in their usage and not get outdated by the time.
It's an interesting point, because certainly just simply the way they work in terms of training, the longer they're exposed to data, the better their quality of the result. That's for sure. The question will actually be the latitude, the scope. At what point will narrow AI not be so narrow? And I think that's the interesting question.
Thank you very much, gentlemen. It was very interesting talking to you, and I wish you a good show.